Hi there, welcome to this video. Thanks for clicking on and watching. Hopefully you've done so because you're studying Maths Edexcel A-Level this summer and paper 2 is on the 14th of June. Here is the list from the exam board of the advanced information, and in this video I'm just going to go through some of the topics and go over some questions and how to answer them. So just before we get started, if you are finding the content of this video useful and helpful, which I hope you are, and your revision is going well, do give it a like and subscribe. Check out my other videos. I have done a few other ones for pure paper 2 and some for the applied paper as well. So before we get started, just going to have a little look in particular at the a to the x function. It's not a major part of the A-level syllabus. You might have met it and looked at the derivative of it. Some of you might have looked at the integral, but it is specified on the advanced information, in particular the function a to the x. So let's have a little look at the graph. So to get a feel of the shape of these graphs, they're exponential graphs. If we just do y equals 2 to the x and see what's going on with when we have 2 to the x, remembering that a is a constant. So if we look at negative numbers, say maybe -2, -1, 0, 1 and 2, just to get an idea of what's going on. If we've got y equals 2 to the -2, this minus here just means it's going to be underneath, and it's going to be 1 over 2 squared, which is a quarter. So you can see even when the x's are negative, the y value is not going to be negative, because that minus, when it's in the power, is just going to put it underneath. So 2 to the -1 is going to be a half. When you have y is equal to 2 to the 0, anything to the 0 is going to be 1, and then we'll have 2 to the 1, 2 squared is 4, and you can see it's going to just exponentially grow because we're going to have the powers of 2 all going up. So this graph is just going to come up, and then it's going to get really much steeper as it goes up, and that is y equals 2 to the x. Now that all the exponential graphs all go through 1, because when you're on the y-axis, the x is going to be 0, and anything to the 0 is going to be 1. So what does y equals 3 to the x? Well, if you think for negative numbers down here, you'll get a ninth, a third, and so on. So it'll be slightly lower here, but it'll still go through 1 and then come up here and grow a bit more rapidly, 3 to the x. Now, what is that special exponential graph that is in between the two of them? Y equals e to the x. That is somewhere in between those two, and that's the natural exponential function. And you should know about the derivative of that. When you differentiate e to the x, it actually maps onto itself. So it's the one function that does differentiate, and the rate at which it grows is exactly the same as the function. So how do we differentiate a to the x if we have y is equal to a to the x? Now, because that x is in the power, we're going to use our log laws and take ln's to both sides, and then log laws to bring that power down. So taking logs to both sides first, the ln of y, logs to that side, is the ln of a to the x. Then your power rule from your logs means you can just move that x down. Ln of y is equal to x, the ln of a. And now we haven't got y the subject, but we can differentiate implicitly. So that means we need to differentiate with respect to y, which is 1 over y. But because it wasn't x, we then just multiply it by dy by dx. Now, how do we differentiate x, ln of a? Remembering that a is a constant. So we have got really a constant times x. So if you had 2x, how would that differentiate to? It would just give you the 2. So x ln of a just differentiates to ln of a. So that's just going to be ln of a on the right. And now we want dy by dx on its own. So we can cross multiply and take that y up. So it's going to be y, the ln of a, and then dy by dx. What was y originally? It was a to the x. So this is just going to be a to the x ln of a. So you can just quote, if y is equal to a to the x, then dy by dx is just a bit like the exponential function, just write it again, but then multiply it by the ln of that base. Now, how do we integrate a to the x? We don't know how to do that, but we do know how to integrate e to the x. E to the x integrates and differentiates just to itself. So we need to find a way of replacing the a, and if it was base e instead, that would be helpful because we do know how to integrate and differentiate that. So what we can do is say e to the ln of a. Now the e and the ln just cancel each other out, and so they are the reverse operations. That would actually equal a. So instead of having this a as the base, we're just going to replace it with this. So it's going to be the integral of e to the ln of a all to the power x. That is what we're going to integrate instead. So we can multiply these two together, remembering that ln of a is just a constant. When you've got 2 cubed all squared, you just multiply those together. That would be 2 to the 6. So this is going to be the integral of e x ln of a dx. Now when you're integrating e to the x here, you do get back just e to the x, but when you're integrating e to the kx, then you get e to the kx, but then you have to compensate for the fact that when you differentiate, you'll have the k in front from the chain rule, and you have to divide by that k to compensate. So this is just going to integrate to e to the x ln of a all over that constant, which in this case is 1 over the ln of a. Now if we just reverse the process and put it back in terms of what it was, because we want to get rid of the e's now, this is just going to be 1 over the ln of a, e to the ln of a all to the x again, and then that is just going to be 1 over the ln of a, and then e to the ln of a. Those two cancel, and we're just going to get back our a to the x, and of course we'd have our constant of integration c. This is a trapezium rule question, and I'm just going to talk a little bit about the trapezium rule before we start. You should remember from GCSE, the area of a trapezium is half a plus b times h. A and b are the two parallel sides. So when you did GCSE, a lot of your trapeziums were this way, a and b, and h is the distance between them. Now when we talk about strips, the strips are the actual trapezium. So this is a strip, and so on and so on and so on. So my diagram here, just to tell you a little bit about it, has got 4 strips. In this question we're just going to do 2 strips, but you can see that the parallel sides, when we draw the trapezium, these are our a and b, the parallel side, and what we need to do is make each trapezium an equal width h. So these should all be equal width h along. And then what we're going to do, the area under the curve is just going to be the summation of all those trapezia. So you're going to have a half h, and then instead of calling them a and b, you call them y naught, because this is y high, and then this is y1, so high, y2, y3, and y4. Now because we start at y naught and we've got 4 of them for 4 strips, there's actually 5 of these vertical lines, and they are called ordinates. So we've got 5 of them, 1 more to make the 4 strips. So if we just look at this one trapezium, this is going to be our y0 and our y1. So putting them into the formula, it's going to be y0 plus y1. And then if we did our second one, it would be half h again, y1 plus y2. So you can see this y1 ordinate is shared in this trapezium and this trapezium, and all the ones in the middle are. So if we start adding up all of these trapeziums, they're all going to have common factors. They've all got a half h, so we can take that out on the front. And then you're only going to have one of the first ordinate and the last, so it's going to be y0 plus yn if we want to make n strips, plus twice of all the ones in the middle. And that'll be n minus 1, and that is the formula that you get, and that's going to be the approximate area using the trapezium rule. So let's try and apply that to this here. We've got a function going from 0 to 4, trying to find the integral of 1 over 2 plus root x. We're being asked to use the trapezium rule with 2 equal width strips. So let's have a little look and draw some x, y coordinates to see what's going on with this function. We have from the beginning of our function 0 and then 2 strips. If we go halfway along 2 and 4, and let's find the y value. So when x is 0, you're just going to have a half. When x is 2, you're going to have 1 over 2 plus root 2, and when x is 2, you're going to have when x is 4, you're going to have 2, so that will be 1 quarter. Now if we draw a graph of what this looks like, when x is 0, we're going to have a half here on the y-axis. It's going to come down to here. When x is 4, it will be a quarter, and halfway along is 2. Now we want 2 strips, so we're equal width, so that's 2 there and 2 there, and so using our trapezium rule, the area is going to be approximately equal to half. Now what is our h? Our h is the equal width along the x-axis, so that's half times 2 times, and then in brackets we need our y0, which is going to be this answer here, half plus twice times the one in the middle, so twice times, we just put it underneath, can't we? 2 plus root 2 plus, and then one of the end ones, a quarter. So these 2's will cancel, and we're going to get that this is equal to a half plus a quarter, 3 quarters plus 2 over 2 plus root 2. Now if I rationalize the denominator on this second fraction and times it by 2 minus root 2 over 2 minus root 2, I'm going to have 3 quarters plus, multiplying that 2 in on the top, you're going to get 4 minus 2 root 2 all over 4 minus 2. So we've got 3 quarters plus 4 minus 2 root 2 all over 2. So this will be 3 quarters plus 4 over 2 minus 2 root 2 over 2, and they will cancel. 3 quarters plus 2, that's 8. Now that's going to be 11 quarters minus root 2, which is what we're trying to get to. Right, part 2 for this question is quite tricky. We've got to use the substitution that x is equal to u squared, and then later on we're going to need the fact that we've just got from the trapezium rule that the area was approximately equal to 11 over 4 minus root 2. So I'm just going to leave that there, and we'll come to that in a minute. So we need to use the substitution. So when you're doing substitution, you need to substitute for the dx all of what's in the integral and the limits. So if x is equal to u squared, we can see that we need to substitute in the integral, that it's root x, so root x is just going to equal u. Now I need to substitute for the dx, so I'm going to have dx by du from my first line here is just 2u. Now dx by du isn't a fraction, but it can operate like one, so dx is equal to 2u du, so that's going to substitute in for the dx. Now I just need to do my limits when x is equal to 0, we can see root 0, u will equal 0, and when x is equal to 4, root 4 is going to be 2. So I'm going to be integrating between 0 and 2 of 1 over 2 plus u, and then times by 2u du. So let me just rewrite that with this being involved over here. What actually I'm going to do is put that 2, this 2 here on the outside, and just have u over 2 plus u du between 0 and 2. Now this doesn't really look any easier. It's easier when we've got more in the numerator and just like a single term on the bottom, and then we can split it up. But in here we haven't really made life that much easy because we've got 2 terms on the bottom. But what we can do here, a little trick, leave that 2 out there. We can say we're going from 0 to 2 of 2 plus u minus 2. So these 2's that I've added and taken away will just cancel with each other. I've not made the fraction on the numerator any bigger or smaller. I've just added 2 and taken away 2. Now we've got more in the numerator, so I can split it up. So I've got that 2 on the outside, and I'm going to have 2 plus u over a 2 plus u minus a 2 over a 2 plus u. So I'm just splitting it up here and having this numerator over the common denominator and this numerator over the common denominator. And here you can see why I've done that is because this is just equal to 1. So it's 2, the integral between 0 and 2 of 1 minus 2 over 2 plus u du. And now I can actually integrate. So I've got my 2 on the outside. I'm integrating. The 1 will integrate to u minus 2 the ln of 2 plus u. And we're going between 0 and 2. So leave the 2 on the outside, starting to put my limits in. We've got 2 minus 2 the ln of 4. The other limit in, 0, will be 0 minus 2 the ln of 2. Now the ln of 4 is the ln of 2 squared, and that's the ln of 4. And what I can do using my log laws is put that 2 in front. So this 2 ln of 4 is really 2 the ln of 2 squared. The square on the 2 can come down and join in with this. So I've got 2 minus 4 the ln of 2, and then this minus minus will make a plus 2 the ln of 2. So tidying up, we've got 2 down 4 lots of ln of 2 and back up 2 will be minus 2 the ln of 2, and then I can take my 2 in and have 4 minus 4 the ln of 2. So that's the actual answer to this integral. Because in part 3, using your answers to part 1 and 2 show that ln of 2 is approximately equal to this k plus root 2 over 4. So we've got an actual answer that involves the ln of 2, and it's the actual answer from what we approximated that integral to be in our trapezium rule. So we can say that 11 over 4 minus root 2 is approximately equal to our 4 minus 4 ln of 2. And now all I need to do is get that ln of 2 on its own. So I can see it's a minus this side. I'm going to take that to that side and say 4 the ln of 2 is approximately equal to 4 minus 11 over 4 plus the root 2. 4 the ln of 2 is approximately equal to 4 is 16 quarters minus 11 quarters is going to be 5 quarters plus root 2, and then all I need to do is divide by this 4. The ln of 2 is approximately equal to 5/16 plus root 2 over 4. So here my k is equal to 5 over 16. Now, just to add on a little bit on the end of this question, it wasn't part of this question, but one thing Edexcel do sometimes like to ask is to find the percentage error. So given that we found as an approximation from the Trapezium Rule that the area was going to be 11 over 4 minus root 2, and then the actual from the substitution was 4 minus 4 ln of 2. So if we take them away from each other, so find them as decimals on your calculator and just take them away from each other and do the biggest minus the smallest, you just need to find the absolute difference between the two regardless of sign, and that comes out to be 0.108374, and you always divide it by the actual, which in this case was 4 minus 4 ln of 2. That would get the difference between them as a fraction of what it was meant to be, and then you just times it by 100. So in this case, if you do that on your calculator, it is 8.83%, so 3 significant figures. So when you're trying to find the percentage error, you find the difference between the two by taking the smallest away from the biggest. So it doesn't matter which one or what order that is, as you just get the absolute difference on the top divided by the actual, so get that as a fraction of what it's meant to be and times it by 100 to make it a percent. Here's a question on differential equations and starting with your partial fractions. So we've got a 2x minus 1 over x minus 1 and 2x minus 3 in the denominator, and we're being asked to put that in partial fractions. So two linear factors on the denominator, a over x minus 1 plus b over 2x minus 3. Now usually when you have partial fractions and you're then going on to do something else, they do give you an easier partial fractions, but you never know, there might be a difficult one with repeated factor, or it might be a top heavy partial fractions question, but this one is just an easier one. Anyway, going clear of fractions, if you multiply by this common denominator, you're going to have 2x minus 1 is equal to a, and then it will have the denominators it's not got with those constants, and then we just let x equal values to make those brackets 0. So we've started with the easy one, let x equal to 1 on the left. Double 1 and minus 1, you'll still have 1, and on the right, if x is 1, you'll have just minus a, so that will tell us that a is equal to minus 1. If we let x equal 3 over 2 to make this bracket equal to 0, we'll have double 1.5, which is 3, minus 1 will have 2 on the left. The a term will go out, and we'll have 1.5 minus 1, which will be half b, which will tell us that b is equal to 4. So writing them as partial fractions, always remember you've done the work. Let's go and write this single fraction as partial fraction. So because the 4 is positive, I might put the 4 first, the 4 term, and that was over the 2x minus 3 minus the a was 1, but just because that was negative, I'm putting it as the second term just to make it nice and pretty at the front, starting with the positive. But that is our fraction as partial fractions. Then in part B, we're being asked to find the general solution of this differential equation, and we can see that it's a first order differential equation because it contains dy by dx. Now what do we do here? We separate the variables and integrate. So all these terms involve x, they need to come down, and the y needs to cross. So cross multiplying, separating the variables and integrating, we'll have the integral of 1 over y dy is equal to the integral of, and this is the thing that we've just put in partial fractions in part A, but they have got it the other way around. They've got the 2x minus 3 first, and then the x minus 1 dx. So it's going to be the integral of 1 over y dy is equal to the integral, replacing this fraction with our partial fractions. It's 4 over 2x minus 3 minus 1 over x minus 1 dx. Now I can see that this 4, what's going to be good is I had the differential of the denominator on the top, so I would be better if I had 2 there, and because it is meant to be 4, if I just put a 2 there, that will still mean that it's 4 on the top. But now I can integrate. 1 over y integrates to the ln of y is equal to 2 times the ln of the 2x minus 3, and then minus the ln of the x minus 1, and then plus c. Now, instead of writing plus c, because I can see all of these are ln's, my constant, I can just write the ln of c. If c is a constant, the ln of it will still be a constant, so just writing that as an ln. And then using my log laws, this 2 here can come up and be a power. So I've got the ln of y is equal to the ln of 2x minus 3 all squared. Now, because this is minus, that log can go underneath, x minus 1, and the ln of c, because it's plus, that can just go on the front here. So I'll just squeeze it in there. Now, the ln of y is equal to the ln of all this. So I can just raise each side to the e, and I will just get that y is equal to c, our constant, 2x minus 3 all squared all over x minus 1. And that is the general solution of this differential equation, but it's asking me for a particular solution. Now, you have to find that by being given some information about x and y, and we're going to find our constant c, and then we will get the particular solution. So part c, when y is equal to 10, x is equal to 2. So subbing that in, 10 is equal to our c, and then when x is 2, double 2 is 4, 4 minus 3, and then square it is going to be 1, so that's just still c. And then the bottom, when x is 2, 2 minus 1 is still 1, so this tells us that c is equal to 10. So the particular solution is that y is equal to 10 times 2x minus 3 all squared all over the x minus 1. This is a function notation question, and we've got f of x being given in this notation. So f of x is equal to 3x plus ln of x. If you're not familiar with this notation, another way of writing this f of x is just that f such that x maps onto and then the 3x plus ln of x. Now, when you have a comma and these things after the comma, this is just telling you what values you can input into that function. X must be bigger than 0 and x must belong to the reals. So for part A, we're being asked to write down the range of g. Now, whenever it says write down, there's never very many marks. You can and should be able to just write down. But looking at g of x, which is e to the x squared, whenever you've got x squared involved, it's worth having a look at positive and negative values. So if x is minus 2, minus 1, 0, 1, 2, because we should be familiar with e to the x being that sort of shape, but what's happening when we've got squared to this side of the graph? If you think if you've got e to the x and you've got e to the minus 2, that's going to be 1 over e squared. So this is where the graph comes down. But when you've got minus 2 and you've got e to the 4, then it's not going to be 1 over. So when we've got e to the x squared, the squaring means that they're not going to go underneath. That will just be e to the 4. This will be e. When we've got x is equal to 0, you're still going to get 1, and then you'll have e again to the 1 and e to the 4. So you can see you're going to get some symmetry about the y-axis. So if you're not familiar with the graph, always just do a little table and have a think about what's going on. So it's going to go through at 1. It's going to do our usual shape, but of course, because it's x squared, it will be steeper. But on the other side, it will be symmetric. So finding the range, when you're looking at the range, it's where does this graph exist for the output for the y value? So go up and down the y-axis and you can see it only exists above 1. So the range is going to be that g of x is bigger or equal to 1. That is our range. Okay, for part B, show that the composite function, so again we've just got this notation, but it's telling us to do fg, and when we've got a composite function you always do the one nearest first, so that means we need to go through g, and g of x gives us e to the x squared. So wherever we see the input value here and here in f, we need to input the answer that we've got when we've been through g. So f g of x is going to equal 3, and then the answer we've got when we've been through g, which is e to the x squared plus the ln of e to the x squared. Now we can see that ln and e are inverse functions. They're just going to cancel each other out. So fg of x is just going to be 3 e to the x squared plus x squared, which is what they've got here, just the other way around. So you could write it the other way around if you wanted to. Now it says write down the range of fg. Now we've already had a look at the e to the x squared graph. Now multiplying it by 3, if we just think of this point here, when x is 0, we're going to get e to the 0, which is 1, but multiplying it by 3, that's just going to give us 3. And then if we add on to that at that point, x squared, if x is 0, then it's still going to stay at 3, but for all the other points, the adding on x squared is going to shift the graph up when we plot the y value. So the graph's going to look similar to our other one and come down like this, but then the minimum point there is going to be at 3, so the graph is all going to exist above 3, so the range fg of x exists all above 3. Now being asked to solve the equation, we need to differentiate fg and equate it to this function expression on the right. So differentiating fg of x, we've got this here, so d by dx of fg of x is equal to 2x plus, now when we're differentiating 3e to the x squared, the 3 is just going to join in. The e to the x squared is a function of a function, so we're going to use the chain rule. So differentiation with respect to the e first, you're going to have 3 e to the x squared. Now you haven't differentiated with respect to the x squared, so that's going to be multiplied by 2x. So let's tidy that up. 2x plus 6x e to the x squared is what we're going to get when we differentiate, and it's asking us to equate it to x into x e to the x squared plus 2. Now your strategy when you're solving this sort of question is to get everything to one side and equal to 0, and I can see that these two terms here have a factor of x, so I'm going to put a 0 here and still have my x on the outside here, but then put these two terms inside the bracket because they're going to be multiplied by x as well. So we've got x e to the x squared plus 2. These two terms, when we take them over, will be minus, so we'll have a minus 2x, but they've taken the x out here on the front, plus a 6 e to the x squared. Again, that x is already out here on the front, and that's not plus, it's minus, isn't it? We're taking it to the other side. So now these twos will cancel in the brackets, and we'll have that x into our x e to the x squared minus 6 e to the x squared is equal to 0, and then we can take e to the x squared out. So we've got x e to the x squared, and then x minus 6 is equal to 0, and solving that, e to the x squared can't be 0, but this x on the front can be 0, so x is equal to 0, or what x value will make the bracket 0? X is equal to 6. thanks for watching. If you're still with me at this point, hopefully you found that video helpful. Please do like and subscribe, and I will see you on the next one.